Hello everyone. So in this tutorial, we are going to talk about maximizing and minimizing strategies. Those kind of questions are usually pretty tough on GMAT and involve some math but a lot of logical reasoning. I'm going to cover here the math portion of it. The logical reasoning portion of it is usually up to the question, and as usual we are going to take an example to apply some of these concepts at the end. So our first strategy in these kind of questions is always to find some way to express the variables or numbers in an equation, right? And one possibility is the variables would be in sum. So we start with the case one. Let's say there are three variables, a plus b equals z. That's the equation we came up with. What would we expect when we are trying to maximize or minimize? Let's say we have to maximize or minimize z. The expectation is that as we increase a, z will increase, right? So if we maximize a, z will maximize. As we increase b, then z will maximize. And then basically if you combine this, then both increasing a and b will result in increasing z. And it is exactly opposite for minimizing, so we won't cover that here, but basically if you minimize a and b, then the z would be minimized as well. A slightly different case when the sum is a constant instead of a variable like z here. So let's say the sum is constant, and now we have to figure out what to do with a and b and how the equation works. It's very obvious, right? So this quantity is now fixed. So if I increase a or maximize a, I have to automatically minimize b, and the other way around. If I increase b, then a will decrease. So if I have some way to find b minimum, then I can find a maximum, and vice versa. Again, it's very intuitive, but when you start applying it in the question, it starts becoming a little complicated. If the number of quantities is a lot more than just 2 or 3, then it gets more complicated. So here we have a minus b equals z. As is very clear, what would happen is if I increase a, my z will increase, right? If I increase b, my z will decrease because b is a negative. If I decrease b, my z will increase. And finally, if I decrease a, my z will decrease. Now let's see what happens when I do something to both a and b. So if I increase a and I also increase b, I don't know what will happen. It depends on how much they increase. If I want to keep z constant, then definitely I have to increase both a and b, otherwise the difference between them would be higher, so z would not be the same. I have to, let's say, maximize z. How can I really maximize z? I can maximize z by increasing a to its maximum and also decreasing b to its maximum. How do I know that? Let's look at where z increases in each case. So this is one case where I'm increasing a and z increases. This is another case when z also increases. So to maximize z, I can do both the cases and then I get the maximum value of z. If I flip it, if I want to minimize z, then I look at the cases where z is getting reduced. So if I increase b, z gets reduced. And if I decrease a, then z gets reduced also. So if I were to minimize z, I would increase b and reduce a. And then I would get minimization of z. That will be my strategy if I'm trying to find maximizing z in this particular scenario. Slightly different when the quantity is fixed. So now it is given that a minus b is 50. So z is not a variable anymore, it is a constant. And you can imagine that if I increase a, what would happen to b to keep it to 50? I would have to increase b too. Otherwise, the difference between them would be more than 50. Same thing on this side. If I reduce a, then I have to reduce b also. The maxima and minima in this case for a and b kind of goes hand in hand. If I increase a to its maximum, I will find B to its maximum. If I increase A to its minimum, I will find B to its minimum because they are going together bound by this difference of 50. Product of two numbers, this is our case 3, follows kind of the same pattern as the sum. So I will leave this as an exercise for you to think through it. It is not very different than what you see in a sum of two numbers. Same thing with division. The way division works is very similar to how you think about difference or subtraction. That brings us to this question from Veritas Prep. It's a very, very good question to demonstrate these kind of concepts. And it is about 4 friends. The 4 friends, they go to Macy's for shopping to buy a top each. 3 of them buy pillowcases. Also given that there are 7 items now, 4 tops and 3 pillowcases, and they're all different integers. And also given is that every top costs more than every pillow. So let's break this down before we go any further, because this is a lot of information. So on the right hand side, I just noted down that there are 4 friends and each of them bought 4 tops and these prices are different. And let us make another assumption that it is in increasing order, and same thing happens with the cost of the pillowcase. So what is given that they are not equal, so that's why the inequality holds, and I have arranged them in increasing order. And also there is one more thing given: every top costs more than every pillowcase is greater than P1, P2, P3. T1 to T4 is greater than P1 to P3. There is another information that is written. All of these have to be integers. All right. And the question asks us, what is the price in dollars of the most expensive pillowcase? So P3 is the real question. What is the value of P3? So we have to find, or at least the data, we have to find information that the data is sufficient to give me a unique value of P3. If I can't get a unique value of P3, then this doesn't work, right? It's not sufficient. And what is also given to us that the sum of the price of 7 items is $89. So let's write that down as well. So sum of the 7 items is $89. And let's apply a little bit of maximizing and minimizing rule we just did onto this one. So let's call the sum of T to T4 as T and the sum of P1 to P3 as P. And this, as we know, is given to be equal to 89. Now, what do we know? We know that if we were to increase T, P will go less to keep the sum as 89, which means if we maximize T, it will be minimum value of P. And if we minimize T, it will be the maximum value of P. So in statement 1, it says the most expensive cost is 16. So we are given this T4, right? We are given T4 equal to 16. So let's rearrange our equation a little bit. So we have the sum of the 3 T's plus the sum of the 3 P's, which we called P here, as 73. We also know something very, very important, that all of these T6 numbers would be less than 16 because all of the P's are less than T's and T4 is the maximum. So we know that T3, T2, T1 would be less than 16. We also know they are integers and we also know they are distinct. Again, same thing applies. If you maximize this, you are going to minimize P. Let's start there, right? Let's make it a starting point and say, okay, we want to maximize T1, T2, T3, the sum of them. T3 would be the biggest of them. T3 cannot be 16. Maximum value of T3 could be 15. That makes the values of T to be these numbers. And if you take the sum of it, you will get that 31. So again, we took the maximum possible values of T1, T2, and T3. We came to this conclusion that P1, P2, and P3, the sum is 31. We again don't know anything about P1, P2, and P3. However, let's start looking a little bit more because we do know some things about P1, P2, and P3. P3 is the highest. The sum is 31. These are 3 distinct numbers. So if they were all equal, let's just say they were all equal, then the quantity would be 31 divided by 3. somewhere in the range of 10, right? So let's assume the P2 is 10, right? That automatically makes P1 as 9, and 10 plus 9 is 19. So that makes P3 as not 11 but 12. That's one possibility. Now let's look at, okay, can I rearrange it a little bit more? So let's say if I reduce this to 8, I can increase this to 11, and I can keep this as 12. So P3 doesn't change. I can do something more. I can say, let's say I make this 8, I keep this as 10, and then what would happen to P3? To keep the number as 31, this will become 13. But can this be 13? It can't be, right? Because T1 is already 13. So it has to be, P3 has to be less than 13 based on this property right here. So it can't be 13. So you can't actually increase P3 beyond 12. Means that we have figured out a maximum value of P3 here, right? In this case where T4 was given to be 16, we have figured out the maximum value can be 12. Can P3 be 11 though? So let's take 11, 10 and 9 for example, but then the sum is only 30. Sum cannot be 31. So 11 cannot be the value, which means we are stuck with only one value of P3, which is 12. That is also the maximum value of P3 and also the minimum value of P3, because you can't go below that. This is it. So hence you get a unique value of P3. So statement A is sufficient. Let's look into statement number B. We look at statement B, and in statement B, we are given that the least expensive pillow, which means this P1, is given to be $9. P2 plus P3 would be 80 because I took out 9 from the. This is given. How many quantities are this? About 6 quantities. If these are 6 quantities and the sum of these quantities is 80, their average is going to be about. So we know these quantities hover around 13. They could of course be more or less than 13. Assume that we had been given A. We know that one of the solution was this. The condition that the P1 should be 9. So let's just say that, okay, this is a possibility. Is there any other possibility? Absolutely. If I want to keep the sum same, I reduce this by 1 and I add plus 1 here. I get 17, 9. This is also a possible combination. So by that itself, I can say that B is not sufficient because I can get two different values of P3. Hence, B is not sufficient. The answer to this question is A. Very good question. I hope this helps. We'll solve more maximizing, minimizing problems in the next few sessions.